Okay, this is homework for chapter 4. I have a battery with an EMF of 9 volts. Let's draw this picture. Here's my battery. It has an EMF equal to 9 volts. And then it has an internal resistance, which I'm going to call little r. So this is the picture of the battery. It is an ideal source of EMF plus the internal resistance. Every battery has an internal resistance. And when you hook this up to some other resistor, light bulb, motor, whatever, this particular one has a resistance of 72 ohms, you get a current flowing in the circuit of 0.117 amps. That's your 117 milliamps converted into SI units. Move the decimal 3 places to the left. So I want to know what is the internal resistance of the battery. I know that the potential provided by the battery minus the drops in potential in the two resistors. So I'll call this delta VR minus delta V big R, where this is big R, is equal to 0. All right, this is a writing of the loop rule, though we haven't called it that yet. So the sum of all the changes in potential is equal to 0. So I can just put this in. I have 9 volts is my EMF of the battery, minus V is equal to IR, that's Ohm's law. So delta V for little r is going to be my current, 0.117 amps times a little r, minus 0.117 amps times big R, which is 72 ohms. And then that's equal to 0. And if I solve this for little r, I find that little r is equal to 9 volts minus 0.117 times 72 divided by 0.117, and then that gives me 4.9 ohms, and that's the internal resistance of the battery. It's fairly small internal resistance. Most batteries have a small internal resistance. A 4 ohm, 8 ohm, and 12 ohm resistor are connected in series with a 24 volt battery. What are the equivalent resistance and the current in each resistor? And then repeat for when it's in parallel. So I have a 24 volt battery. Then I have 3 resistors that are hooked up in series with one another. That means that they're one after the other. Just like this. I have 4 ohm, 8 ohm, and 12 ohm resistors. I want to know first what is the equivalent resistance for part A. That's pretty easy. Equivalent resistance is just the sum. That's equal to 24 ohms. So that's my my equivalent resistance. And then I want to know, that means, by the way, that I can replace those 3 resistors with a single 24 ohm resistor. This is 24 volt battery. And now I want to know the current that goes for each resistor. Resistors in series, let me write this. Resistors in series have the same current. Resistors in series have the same current. So each of these resistors have the same current. A certain amount of current entering this point goes through each resistor, and then that same amount of current comes out this point. It's like water flowing through a pipe. If you have a certain amount of water going through a pipe, you're going to have that same amount at any point within the pipe, as long as there are no branches within the pipe. It doesn't split up. So I can calculate this current, and it's going to be the same as each current that's in each resistor. So V is equal to I times R equivalent. And so I through this resistor is equal to V over R equivalent, which is 24 volts over 24 ohms. That's equal to 1 amp, and that's our answer. 24 ohms is our equivalent resistance, and our current is 1 amp for each of the 3 resistors. Now, slightly different scenario where the 3 resistors are hooked up in parallel. Alright, this is 4, 8, and 12 ohms, and they're all hooked up to a 24-volt battery. First, find the equivalent resistance. That is the inverse of the sum of the inverses, 1 over 4 plus 1 over 8 plus 1 over 12. That's equal to, if you find the common denominator, which is 24 over 11, gives us 2.2 ohms. 2.2 ohms. So, the equivalent resistance is 2.2 ohms. Now we want to know the current in each one. Resistors in parallel, it's our rule, resistors in parallel have the same voltage, not the same current. But each of these resistors, the 4, the 8, and the 12 ohm resistor, all have a voltage of 24 volts. So, I can find the current in the 4 ohm resistor is going to be V over R. That's going to be 24 volts over 4 ohms, which is going to be 6 amps. The current through the 8 ohm resistor is going to be 24 over 8, which is 3 amps. This should be 6.0 to keep proper sig figs. And then the current in the 12 ohm resistor be 24 over 12, which is 2.0 amps. Alright, so those are the currents through each of them. Now the question didn't ask this, but notice that if you add up these three currents, if you add up those three currents, that's 6 plus 3 plus 2, that's equal to 11 amps. So that means that the current that is coming here is 11 amps. Now further we can see that, if we draw our equivalent circuit, and this wasn't asked in the question, but just to show you, if this is 24 volts and this is 2.2 ohms, the current coming through here, I, is equal to V over R. That's 24 over 2.2. That's equal to 11 amps. So the current that flows through off of the battery is split into 3 pieces, and when those 3 pieces come back together again, they have to equal the total current. That is, the sum of the currents has to equal the total current in a parallel circuit. That was one of our rules as well. Alright, number 3, a 9 and a 6 ohm resistor connected in series. The voltage drop across the 6 ohm resistor is measured to be 12 volts. Find the voltage output of the power supply. Alright, so part A first. Let's draw our circuit. I have a 9 and a 6 ohm in series. This is 9, 6 ohm, and we're connected to a power supply, but we don't know what the voltage is. We want to know what the voltage is, but we do know that the voltage across this resistor is 12 volts. And we want to know what is the voltage output of the power supply. Well, if we know what the voltage is across that resistor, then we can find the current through that resistor. And the current through that resistor is going to be V over R. That's the voltage drop across that resistor divided by the resistance of that resistor is equal to 2 amps. That means that there is 2 amps of current flowing through that resistor through the 6 ohm resistor. Because resistors in series have the same current, there is also 2 amps flowing through the whole circuit. So now I need to find the equivalent resistance, which is going to equal 9 plus 6, is equal to 15 ohms. And then so if I redraw my circuit like this, I have a 15 ohm resistor and V, and I know that I have 2 amps, so I can find V is equal to I times R. It's equal to 2 amps times my equivalent resistance, which is 15 ohms. So I have 30 volts going across that battery. That's the potential difference of the battery, is 30 volts. Now notice that since we know our current is 2 amps, the voltage across this resistor is 9 times 2, which equals 18. And notice that 18 plus 12 equals 30. This number is the same as this number. 18 plus 12 is equal to 30. Alright, now in the next part, we're supposed to find, it says the two resistors are connected in parallel across the power supply, and the current through the 9 ohm resistor is 0.25 amps. So let's just draw our circuit first. This is our power supply. We have two resistors in parallel. We want to know, again, what is this potential across the battery? Presumably it's a new battery. We have a 6 ohm and a 9 ohm resistor, and I'm told that the current through this resistor is 0.25 amps. 0.25 amps. So I want to find the potential. I know that the potential across the 9 ohm resistor, that's going to be the same as the potential across the 6 ohm resistor, because resistors in parallel have the same potential, or the same voltage. Also, the voltage across the 9 and the 6 ohm resistors are going to be the same as the voltage across the battery. So all I need to do is find the voltage across the 9 ohm resistor, and I know its current and its resistance. It's going to be 0.25 amps times R, which is 9 ohms, which is 9 over 4, which is 2 1/4, 2.25 volts, or 2.3 volts. So that's our answer. That's also the voltage across this resistor, and the power supply. Alright, find the equivalent resistance and find the current and resistance, or find the current and voltage, it should say, in each resistor. So this word should say voltage, or potential, in each resistor. Okay, so first to find the equivalent resistance, we want to start with the smallest branches that are solely parallel or series. So for example, we'll start with this one. Alright, it's only in parallel. Now in contrast, let me just show you something. Well, if we were to look at this total one with the R5 as well, that is not only series or parallel. It is a mixture of series and parallel resistors, because we have R3 and R4 in parallel, and then they're in series with R5. So we're just going to start with R3 and R4, and it has an equivalent resistance, inverse of some of the inverses, 1 over 2 plus 1 over 2, that's equal to 1. Alright, we also want to find the resistance, the equivalent of these two. It's equal to 1 plus 1 is equal to 2. That's how you find the equivalent for resistors in parallel. Now let's just redraw this a little bit. I have a 1 ohm, 1 ohm, and a 2 ohm. Now I want to combine these two, and that gives me an equivalent of 2 ohms. So I'm left with a 2 and a 2, 12 volts here. And I know that this equivalent, just like I did before, is 1 over 2 plus 1 over 2 is equal to 1. So my final equivalent circuit is going to have a resistance equal to 1 ohm. So that's the first answer, is the equivalent resistance equals 1 ohm. This is 12 volts. Now, I want to find the current and the resistance in each resistor. There are a variety of ways that you can go about this, but we'll just start from here. I know that on this circuit, I have a current here equal to V over R. That's going to be 12 over 1, which is 12 amps. So I have a current of 12 amps going there. Alright, I also know in these two resistors here, that my voltage is equal to 12 volts, and my voltage here is equal to 12 volts. Because they're in parallel, they have the same potential. Alright, so I know that I have then, going up to this circuit right here, that I have a voltage equal to 12 volts. And here, on the bottom branch, I have two identical resistors. I have this 1 ohm resistor and another 1 ohm resistor. Alright, so each of those resistors is going to split equally the 12 volt potential. So you see I had 12 volts down here, and now I'm going to have 6 volts across that 1 ohm resistor and 6 volts across that resistor. So I've started to get some of the answers here. I'm going to just write them as I get to them over here. V5 is going to equal 6 volts. That's this value because this resistor is the same as this resistor. V3 and V4, because they are in parallel, are also going to be 6 volts. V3 and V4 are also going to be 6 volts because this equivalent resistance is 6 volts, and these two are going to have the same voltage because they're in parallel. Now, V1 and V2 can find fairly simply because I have 12 volts across their equivalent resistor, and we have two identical resistors splitting that voltage of 12 volts. So they're going to split 12 volts evenly, so they're going to get 6 volts each. Alright, so in this case we found all the voltages, and now to find the currents, well, we know that V from Ohm's law is equal to IR, so I is equal to V over R. So I can just find I1 is V1 over R1, so that's 6 over R1 was 1 ohm, 6 volts, so it's 6 amps. In a similar way, I2 is V2, which is 6 volts, over 1 ohm, which is 6 amps. They're in series, so you'd expect R1 and R2 to have the same current. I3 is V3 over R3. That's going to be 6 over 2, just 3 amps. I4 is 6 over 2, it's 3 amps. And then I5 is 6 over 1, or 6 amps. So those are the answers. Oh, excuse me. Okay, well those were the answers. Sorry about that, but those were the answers. Alright, number 5, find the equivalent resistance of the circuit in this figure. Okay, let's find the equivalent resistance first. Similar, I want to start with this one. The equivalent resistance of this is 1 over 10 plus 1 over 5, and that's equal to 10 over 3, which is 3.33 ohms. Alright, and then we would have a circuit that would look like this. That's my 3 ohm resistor. It's my new 3.33, and then my 4 ohm resistor. And a 3 ohm resistor over here, and then back to the battery. Now I want to combine these two. That's going to be 7.33 ohms. Alright, and then I'm going to combine these two, which is going to be 1 over 7.33 plus 1 over 3, which is going to give me a resistance of 2.13. Alright, let me just redraw this again. There's my first 3 ohm resistor, that's the one that's right here. And then I have a 2.13 ohm resistor, which is the equivalent of that big branch that we saw. And that, of course, has an equivalent resistance, and this is our final equivalent of 3 plus 2.13, which I'll just call it 5.1 ohms. 5.1 ohms. Right, that's my equivalent resistance. And now I want to know the EMF of the battery, and I'm told that the power supplied is 4 watts. I know that P is equal to VI. I don't know the current right off in this circuit. You could find the current and solve it in that way. Or you can say that I is equal to V over R, so this becomes V squared over R. And I want to solve for V. It's going to be the square root of P times R, or the square root of 4 watts times 5.1 ohms. I get 4.5 volts. Alright, so the equivalent resistance is 5.1 and the voltage of the battery is 4.5 volts. Okay, number 6 says the ammeter shown in this figure reads 2 amps, finds V2, I1, and I3. I made some changes to this. I made announcements about this in class. But the new problem, first of all, doesn't say anything about finding V2, because I give you this to be 20 volts. And I move the ammeter from here, so the ammeter is no longer here. The ammeter is right here. So my current, I2, is given, and it's going to be 1.789 amps. And then I also say that the current I2 is in the proper direction, because as you know, sometimes you can choose the direction incorrectly. But in this case, if you find I2, it's going to be positive 1.789. That means that I2 has that magnitude, and it's also flowing downward. Okay, so now I want to find I1 and I3. I can write a couple of equations. I'm going to write the first equation based on the left loop, using the loop rule, and I'll start here, and I'll go around in this direction. I come to the battery. For the loop rule, recall, I do the sum of the voltages is equal to 0. So I have 10 volts minus 3I1. And then I come up, I have plus 20 volts plus 4I2. Plus 4I2. Excuse me, this should be minus 20 volts plus 4I2. And then that's equal to 0. Plus 4I2 is equal to 0. And now I want to solve this for I1. And if I solve this for I1, it's 10 minus 4I2 divided by negative 3. Alright, I combined the 10 and negative 20 volts, and that became negative 10. And then I brought the 10 and 4I2 over to the right-hand side of the equation and divided both sides by negative 3 to get this. And then I put in I2, which I know to be 1.789, and I find that I1 is negative 0.948 amps. Negative 0.948 amps. All right. Now, I know I1 and I2, and I also want to know I3. So the easiest way is to do the junction rule, and that says that IN equals I out. IN equals I out. And IN, I'm just going to pick any junction. And the incoming currents, well, let's see, they're all outgoing. So the incoming currents are 0. And then that equals I1 plus I2 plus I3. I1 plus I2 plus I3. And I'm looking for I3. So it's equal to negative I1 minus I2. And that's equal to negative 0.948. Excuse me, positive 0.948 minus 1.789. The positive is because I1 was negative, And when you put that I1 back into the equation, you have to retain the sign that it had. Okay? We'll deal with the signs in just a moment. And that tells me that I3 is negative 0.841 amps. Okay? So my answer is that I1 equals 0.948 amps. And I initially drew it as being downward. It's going to be up. And I3 is 0.841 amps. And I initially drawn it to be downward, but it's actually going to be up because it came out as a negative value. So those are the answers for number 6. All right, determine the current in each branch of the circuit shown in this figure. This is a multi-branch circuit. You have 3 unknowns. Those are the currents, I1, I2, and I3. Our first step is going to be just labeling I1 and I2 and I3. I'll call this current I1. I'll call this current I2. And I'll call this current I3. Doesn't matter the direction that you give them. You just pick a direction. It doesn't matter which one you call I1, I2, or I3. You just pick one and go with it. And then we want to apply the various rules. I'm going to apply the junction rule first. The junction rule says that the ingoing currents equal the outgoing currents. Let's see, I'll start here. And I have I2, that's the incoming current, is equal to I1 plus I3. That's my first equation. Now let's use the loop rule. I'm going to do the left loop. I'll start up here and go in that direction. I have 10 volts minus 1 I1 minus 12. I'm going up here, coming along here, and then coming up here. Minus 12 minus 2 I2. That's equal to 0. And then I'm going to solve the right loop. I will start here and go up in this direction. So that's minus 12, just like I did before, minus 2I2, and then coming along here, minus 5I3. That's equal to 0. So now I have 3 equations. I want to solve these equations for I1, I2, and I3. So 3 equations and 3 unknowns, so those are solvable. When you look at this, I'm going to solve the bottom 2 equations for I1 and I3, and that will give me I1 and I3 in terms of I2, and then I can plug that back into the top equation and have nothing but I2s. So let me show you. I'm going to solve this one for I1. So this equation becomes I1 equals minus 2 minus 2I2. And then this equation, I'm going to solve for I3, and it equals minus 12 minus 2I2 divided by 5. Right, so now I have expressions for I1 and I3. I'm going to plug those back in to the junction equation. So I'm going to have I2 equals I1, which is minus 2 minus 2I2. That's my I1, plus my I3, which is minus 12 minus 2I2, over 5. So that's just the junction equation with those substitutions made. Let's see, I'll multiply both sides by 5. 5I2 equals negative 10 minus 10I2 minus 12 minus 2I2. That gets rid of that 5 in that denominator. Then I will combine my I2 terms and my numbers, and I get negative 22 equals 17I2. And then solve for I2. It's equal to negative 1.2941 amps. I keep more sig figs than I need because it helps them to work out, to be consistent in the end. 1.2941 amps. I chose I2 up, so I know that I2 has to be down because it came out negative. Now to solve for I1 and I3 is pretty simple. You just plug them back into these equations. I1 works out to be 0.5882. 0.5882 amps, and since it came out positive, we chose I1 to be down, so it is down. And then I3 is negative 1.882 amps. We chose I3 to be down, so it's up because it came out negative. Those are the answers. The currents in each resistor, or each branch. Oh, and notice also that I1, the current I1 flows from here all the way around through there. That's I1. I2 flows from here up to there, just in that middle branch. And then I3 flows here and here. Those are 3 branches. You have the 2 on the sides and the 1 in the middle. All right, consider a series RC circuit. C is equal to 6. R is 2 mega ohms, 2 times 10 to the 6 ohms. And E is equal to 20 volts. Find the time constant. All right, with tau, that's the time constant, is equal to R times C. That's 2 times 10 to the 6 ohms times 6 times 10 to the minus 6 farads. You have to convert them back to SI units. The 10 to the 6's cancel, and so I'm left with 12 seconds. So my time constant is 12 seconds, and then the maximum charge on the capacitor after a switch in the circuit is closed, not dosed, it should be closed. So this is when I'm charging the circuit. And you know, when you charge a circuit, if I was to plot the charge versus time, it's going to look like this. After a certain amount of time, after approximately 10 times the time constant, so in this case after 120 seconds, we're going to reach some maximum charge. And that maximum charge is just C times V. And the capacitance is 6 microfarads. The voltage is 20 volts. So this is going to be 120 microcoulombs. There's my time constant. There's my maximum charge. Okay, consider this RC circuit. R is 1 mega ohm, C is 5 microfarads, E is 30 volts. I'm the charge on the capacitor 10 seconds after the switch. All right, let's just check our time constant right quick. It's RC. R is 1 mega ohm. C is 5 microfarads. So my time constant is just 5 seconds. Notice what I did here. Mega is 10 to the 6. Micro is 10 to the minus 6. Often your resistance is in mega ohms and your capacitance is in microfarads. So the 2 units, or the 2 metric prefixes, cancel one another out. 10 to the 6 over 10 to the 6 is 1. So my time constant is 5 seconds. So my capacitor is not fully charged. Again, if I plot Q versus T, it's an exponential function like this. This time, right over here, is approximately 10 tau, which is 50 seconds. But I'm looking at a time of about 10 seconds. So I want to know what is my charge right over here at about this point at 10 seconds. All right, so I actually have to look at the exponential function that describes this relationship, and it is that Q is equal to Q naught times 1 minus e to the minus t over the time constant, or RC. So I can, Q naught is just the maximum charge times 1 minus e to the minus t over tau. And this is 5 microfarads, my capacitance. 30 volts. Right, yeah, 30 volts times 1 minus e to the minus 10 over 5. And you plug that in, and you find that it's equal to 130 microfarads. I've been a little loose with my metric prefixes. You notice I didn't convert my 5 microfarads to farads, to 5 times 10 to the minus 6 farads. That micro just sort of carries down through. And so if I just leave it in microfarads, then I know that my final answer is going to be in microcoulombs. It should be coulombs, 130 microcoulombs. You should make sure that you can use the exponential function, that you know where it is and how to use the exponential function. So just make sure in your calculator that you know how to input these numbers correctly. Our electric heater is rated at 1300 watts, toaster at 1000, and electric grill at 1500. The three appliances are connected in parallel to a common 120 volt circuit. How much current does each appliance draw? Is a 30 amp circuit breaker sufficient in the situation? Alright, so we just want to find the current for each of them. I know that P is equal to V times I. V is equal to 120 for all the devices, and so my current is P over V, or the power of each device over 120 volts. So let's see, I have my heater, my toaster, and my grill. And I want to find the current, which is P over V. So for my heater, that's 1300 watts over 120 volts. That's equal to 10.8 amps. For my toaster, it's 1000 watts over 120 volts. That's equal to 8.3 amps. And my grill, it's 1500 over 120. And then that's equal to 13 amps. Alright, so I want to just add up all these currents. These are all in parallel. Your household circuit is laid out as a parallel circuit. So the total current is just the sum of all the currents. And if I add up all these, it's going to be 32 amps. That means if you were running your heater, your toaster, and an electric grill all at the same time, then it's going to kick a 30 amp circuit off. So B, no, a 30 amp circuit isn't sufficient because 32 amps, which is your load, is greater than your maximum allowed load on the circuit breaker. So your circuit breaker is going to kick off and everything's going to go off.